morning, ladies and gentlemen. So actually today my presentation covers so many sections. I would try to be short because normally it's taken hours. First of all, I would present you and highlight the first four main areas from where the most challenges, requirements, and the technical tasks are coming from. So, of course, there is electronics areas, mostly related to electrical conductive properties, mostly with the high elastic properties, lightweight, and any advantages which could be brought by the carbon nanotubes. The second one is the tires industry, where the wet grip, abrasion resistance, and fuel consumption hysteresis losses reduction is required. The next one is the oil and gas industries, where the high durability and different resistance to other properties is required as well. And the last one is the automotive, particularly electric vehicles industry, which require the highest durability now because of the different requirements, and I would say even totally different requirements for the new particular rubber goods for this particular industry. Today I will present you and highlight some new directions in terms of the carbon nanotube development for elastomers area. So it's a well-known fact that the most challenging and the most important is the dispersion process. In this particular case, we're using the different sort of the plasticizers and particular carriers which is commonly used and user-friendly to the formulations, but let's say in terms of the 90% of the cases for the master batch carriers, it's normally uses some sort of plasticizer, oils, release agents, and so on. So normally these carriers has some sort of very significant drawbacks in terms of mechanical properties and quite limited in terms of the concentration because of that drawbacks. So according our, let's say, current plan and the new plan, we are developing the new carriers for the master batches, which is commonly used in the industrial areas as well as the has a very good interaction with the carbon nanotubes and could be properly dispersed in the standard industrial process. This is a low molecular polymers, which is commonly used in the elastomer and particular tire industry, which has no significant drawbacks because it's very familiar to the elastomer formulation. It's quite universal in terms of the type of the formulations, and there is no extractable plasticizer which will go out to the surface during the cycle life of the particular rubber goods. There is no environmental exposure, so that means it's some sort of environmental friendly plasticizer. What is related to the new development of these particular liquid polymers, we started, of course, with some sort of the conductive applications, where first of all required three main properties. There is an anti-static, no drawback in mechanical properties as one of the main, let's say, targets, and of course the color. So the main target was to choose the right carrier. That means the compatibility with the formulation, viscosity, and interaction with single carbon nanotubes. So currently we developed few range of the master batches based on liquid polymers related to the conductivity and EPDM. We divided that into parts for the high Mooney viscosity and low Mooney viscosity EPDM, as well as the FKM. Actually, it was evaluated with required anti-static level with a bright color and the maintain of the elastic properties. I would say a few words regarding the high resistant rubbers in the different synthetic rubbers areas. So currently we are approaching this area into two ways. First of all, it's the introduction through the master batch route, and the second one is the introduction into the polymer synthesis process, which we call in situ. So today I will present some results very briefly in terms of the in situ polymerization with a different concentration of the carbon nanotubes. This particular process was covered by dispersion route. It's a polymer synthesis where the toluene dispersion were used. So currently, at this slide, you can see the TJ data in isoprene rubber, where the heat resistance presented. So at this slide, you can see that the temperature resistance area, where the 5% of the degradation of the polymer was investigated. And here actually you can see that go back. So with the highest dosage as much as possible, we introduced the from 50 ppm to 2000 ppm of carbon nanotubes by the polymer content. And here in this slide you can see how many degrees of the polymer degradation from the 5% to 10% was improved with carbon nanotubes. So, and you can see that as much as higher content of the carbon nanotubes, you can see that significant improvements in the temperature degradation from, let's say, up to 51 degrees. And the average is 33 degrees. Yeah. So, and the same trend we actually realized in the NVR rubber, where the completely different synthesis types were used, because it's quite important, because the previous case it's solvent-based rubber, and in this particular case it's emulsion rubbers. That means in both types of the polymerization we see that the same trends, and this is, let's say, for us, it's further development directions. Few words regarding the conductive applications and some specific cases which is related particularly to the carbon nanotubes. This is a well-known fact that most of the elastic or elastomeric materials uses with some sort of the different forces and the different directions of the, let's say, elastic applications. And the question is how long the conductive network can provide the stable properties. Because currently we're talking about carbon nanotubes, it's a very low concentrations. That means it's not really properly developed and the properly, how to say, searched. In terms of the R&D, how much these properties is really stable during the real industrial process. So here I would like to present the conductive properties and the different dynamic deformations. You can see that the blue line is before deformations. This is particularly LSR with the antistatic properties, and how the electrically conductive properties works in terms of the different dynamic deformations. Here we're talking about 100% the tension. So you can see that exactly after tension, it's of course the network is quite destructed. You can see plus a few orders of magnitude, but because of these elastomers, it was investigated that up to the, let's say, almost 12 hours, and as well as, let's say, of course, the longer time, it's a relaxation of the elastomer, and we could confirm that the resistance and the required antistatic level after the relaxation confirmed that at the same antistatic level. So that means the material is relaxated after the dynamic deformation. That is quite important in terms of the particular application and in terms of the stability of the conductive properties. Same or similar trends, quite similar, was confirmed for the conductive LSR, which is also important because we're talking about the different concentration of the carbon nanotube. So after 87 hours, it's almost the same order of magnitude after the relaxation. And very good comparison to the carbon black based solutions. So here we compare the matrix 605, particularly in HCR, together with the most commonly used solutions. It's Elastomers 570 by Wacker, and also the carbon black based solutions with more than 25% of carbon black. There's a same trend in terms of the elasticity and the conductive properties during the dynamic deformation, but you can see in this slide that even after 50% or 100% of the deformation, all the samples based on carbon black were broken. So that means carbon nanotubes could provide the much more elastic properties with the same level of electrical conductivity, which is stable during the dynamical deformations. And the last point I would present and highlight, there is a differences actually where carbon nanotubes can be used, and what is the difference in terms of the different measurement process, because we are talking currently about nanomaterials. It's not only different in terms of the particular size of the active content, but also in terms of the different measurements process. So a particular case is related to the very good example to rubber printing rollers. So normally that rollers has some sort of the surface area treatment after the extrusion. So, and here you can see the data regarding the surface resistivity measurements for the rough surface and uneven surface, some sort of rigid surface. So you can see that the volume resistivity data is exactly the same, but reading for the uneven, let's say, rough surface and rigid surface is quite different, up to, let's say, 4 or 5 orders of magnitude. That's related mostly for the surface area for the electrodes contact. So this particular problem could be used for the right particular measurements, could be used through the 2 ways. First of all, it's a standard NC electrodes, which normally uses, according to ASTM standard, D257, or conductive silver paste or any conductive paste could be used to reduce these challenges in terms of to provide the right contact area and to reduce the high contact resistance. Okay, what's happening when we measure the carbon black based sample and, for example, carbon nanotubes based sample? For the carbon black based sample, it's a well-known fact that there is a carbon release on the surface of the sample. So that means carbon black on the surface makes a role of the conductive paste. That means the readings by the simple devices normally is quite different, and I would say the totally different compared to the carbon nanotubes. In terms of the carbon nanotubes, because of the low dosage, it's completely cured into the polymer carrier. That means the particular surface resistivity reading would be different. That means it's required another way for the measurement. That's why it should be understandable and applicable to the normal industrial process. For the conclusions, I would highlight, let's say, the whole directions I already mentioned. First of all, the additive efficiency mostly related to the right carrier, which should be compatible with the carbon nanotubes, first of all, to get the good interaction, of course, with the polymer. And the target has as much as limited number of drawbacks or even some improvements by the carrier. So impact of the rubber properties to the mechanical so any resistant properties is always also investigated by our company, and this is the first directions for the development in elastomers area. Of course, if we're talking about particularly very different and very specific materials as the carbon nanotubes, we need to mention that existing testing methods not always suits to the particular materials, and this is also should be mentioned by industrial process. So this is actually everything what I would like to highlight today with this short presentation. Thank you for your attention. I would welcome.
Thank you, Kate. Thank you. Any questions?
I'm Ekaterina from Daikin. Thank you for a great presentation. I have keen interest about polymer degradation temperature. So even though adding less than 1% single carbon nanotube, why does polymer degradation temperature dramatically increase? So could you please tell me about the mechanism of this carbon nanotube?
Thank you for your question. So first of all, that's mostly a question related to the R&D directions. It's, to be honest, not really area that was researched so much, but theoretically what was mentioned by the researchers that the polymers covers to the carbon nanotubes, that means it's some sort of an additional stability network, to simplify. But in fact, of course, this particular process and these particular improvements could be investigated much more. This is just, let's say, some sort of the starting points, and the deeper research of the mechanism, of course, will be developed in the further steps of the R&D. To explain how much exactly it could be improved and how is the mechanism.
I'm Albert Carl from TUBALL Aesthetic Technology. Okay, just now I noticed that regarding the test method that you highlighted, that was the ASTM D257. I think the method, I think this should be changed to S2020 test method, because the ASTM D257 actually is to measure the insulated material. So for this carbon nanotube, you should be using the S2020 method. That is the NC ESD standard test method. Just a small correction. Thank you.
Thank you. Actually, yes, we're using the few methods, even ASTM 200-991, some DIN methods and ISO methods. There is just an example, but in general, the mechanism is same. I mean, the ANSI electrodes requirements and so on. Yes, thank you for your correction.
Hello, I'm Tony Ding from Guangzhou, KMK. My question is, I just heard you said you have some research for tire industry. As I know, more and more tire factory right now, they use silica as the reinforcing material due to some environment policy in Europe. So my question is, do you do some research work, and do you have some product for tire industry?
Of course, tire industry, this is, I would say, one of the most important development directions for our company. Of course, we are developing this even specific program and specific products for the tire industry. Now it's, let's say, some sort of the separate program. Of course, we are evaluating particularly for the tire applications, our solutions, of course, which is related to the silica-based compounds, carbon black-based compounds, because that's a well-known fact that the tire formulations is quite different from the company to company. We need to understand, and we are investigating the mechanism, how the carbon nanotubes could be evaluated in terms of the particular commonly used, the passenger as well as the track tires formulations.
Okay, thank you, Sandy. Thank you.